Okay, we're back with the second half of 6.2b, and we've got a few more examples to do to really kind of hone this method of trigonometric substitution. So in our second example, we're looking at an integral of 1 over x squared times the square root of x squared plus 4 dx. Of course, it's always worthwhile to keep an eye out for a u substitution to simplify one of these things. In this case, there just really isn't one. But sometimes there might be. But now we look, of course, we have trouble with a radical. So the idea is to consider a trigonometric substitution to handle that. And we look at the form that we've got then. It's x squared plus 4, which is x squared plus a squared. So x squared plus some real number. So if a squared is 4, then a is 2. So we just want to lay those details out so we're sure about things. Now, since it's x squared plus a squared, we'll use the substitution x equals 2 tangent theta. So 2 tangent theta, or a times tangent theta. And, you know, I always recommend checking this, write x squared plus 4 down, or x squared plus a squared. And when we do that, we've got x squared is 4 tangent squared theta plus 4. In other words, we're just writing down this term, x squared plus a squared, right here on the left, and carrying out what that means in terms of tangent theta on the right, 4 tangent squared theta plus 4. Factor 4 away from both of these. That's why we use a times tangent theta, by the way. And then we've got inside parentheses, tangent squared theta plus 1. And it's just a matter of remembering our Pythagorean identities. But tangent squared theta plus 1 is secant squared theta. So now we've condensed these two terms into a single term, which is crucial for possibly getting rid of a square root sign. So we've got 4 secant squared theta that will sub in for x squared plus 4. So that's ideal. It looks like it's going to work out. Remember, if anybody's asking or thinking at this moment, well, we have the square root of x squared plus 4. Both of those are perfect squares. That is not equal to x plus 2. It doesn't cancel that way. X squared times 4, if we had the square root of x squared times 4, it would be 2x. But certainly we cannot cancel this square root with x squared plus 4 just because those are perfect squares. Consider the square root of 1 plus 3 as a group versus the square root of 1 plus the square root of 3. You'll have two different values there. So don't forget algebra. Anyway, we've condensed to one term. So dx d theta is the derivative of this term right here, taking the derivative with respect to theta, gives us dx d theta, and that is 2 secant squared theta, just a basic derivative. And then we just note that x squared is 4 tangent squared theta, just for that term over here. Again, not necessary, but nice to have around to set up all the details. And now we can plug everything back into this. We have a substitution. We know that dx will be this times d theta, and we know what everybody else will be. And our integral I now is equal to, remember that dx is secant squared theta d theta, so there's our numerator. Oh, and there's a 2 as well, 2 secant squared theta d theta. And moving on, x squared was 4 tangent squared theta, and of course, x squared plus 4 was 4 secant squared theta. And we see these two constants cancel to 1 and 2. And also that radical will cancel. 4 times secant squared will cancel to 2 secant theta. Okay, further cancellations that happen in the next step. Secant squared matches with the secant in the denominator. So we lose one factor of secant from both of those. So the one in the denominator is gone. This one's out. And we just have secant to the first in the numerator. Well, we can continue. We still have tangent squared theta in the base. That 1 over 2, we'll move it out with this 2 in the denominator as a 1 over 4 now. Carefully check those algebraic details, but it should work out. And we've got secant theta d theta in the numerator divided by tangent squared theta in the denominator. Now we can probably get some cancellations out of that. It doesn't hurt to convert to sines and cosines just to see. Secant theta is 1 over cosine theta, so that's written here. Tangent squared theta is sine squared theta over cosine squared theta. But since it's in the denominator, we'll flip it and write it as cosine squared theta over sine squared theta. Or you might have realized that tangent squared in the denominator is cotangent squared, and what we've got written in the line below is exactly cotangent squared theta, this portion here. Okay, and having done so, we see that a factor of cosine cancels here, so cosine squared becomes cosine to the first power in the numerator, and we have no more cosines in the denominator. That's good. So this cleans up to this point, cosine theta over sine squared theta. And we see a nice u substitution. Sine is the more complicated portion in the denominator, so if we let u be equal to sine theta and check, is there a du around for that? Well, the du for that would be cosine theta d theta, and that's exactly what we have in the numerator of this integrand. So that's perfect, cosine theta d theta. This u substitution will work, and we have u to the -2, or 1 over sine squared theta with a du here. So that's u to the -2 for that 1 over sine squared theta, and there's our du. This is even easier than the last integral. Ultimately, we have add 1 to this, divide by the new power. So there's -1 in the exponent, divide by that -1. Just a reminder of the integral power rule. And 1/4 is still out in front. The integral's gone, integral sign's gone, so we have a plus c. And we know that u was equal to sine theta. So we can sub this u out for sine theta. So we're back in terms of sine theta. Be really careful here. Remember that sine theta to the -1 is 1 over sine theta, or as we see in the next line, cosecant theta. This is the only time we don't use that notation, the exponential notation, right here in the exponent of sine, because it would look like the inverse. It is in fact not the inverse. It's the multiplicative, multiplicative inverse, but it's not the inverse function arc sine. So simplifying this to this point, we just need to discover what cosecant theta is in terms of x, and then we'll be able to finish out to our bottom line. So in order to do that, just as last time, we go over to a triangle. We just happen to have room at the top of the page. It's also convenient to do it up here because we remember that x was 2 tangent theta. This is our critical link between x and theta. It's the first one we write down. It's kind of the last one we'll use. So we've got x equals 2 tangent theta. Now remember that that's x divided by 2 will be equal to tangent theta then. And that's what we have written over here. So x over 2 is tangent theta. Remember that tangent theta is opposite over adjacent. So if this is theta down in this corner, then the opposite of x is over the adjacent of 2. And this is a squared and b squared over here. So we've got x squared plus 2 squared is equal to c squared. But to solve for c should be the square root. Right? So now you can check that this squared plus this squared, the square root of that is equal to c. Or you could say this squared plus this squared equals this term squared, because when you square that last term, the radical goes away. So in fact, it is correct. Anyway, that's just a little review of trig to try to make students feel a little better about things. We need to know what cosecant theta is. So cosecant theta, remember, is hypotenuse over opposite. It's the flip of sine theta. So hypotenuse is this term. So it's square root x squared plus 2 squared is 4. So we can go ahead and rewrite that. And by the way, that term's showing back up again. Should make us feel pretty good about things. That'll be pretty typical. And then divide by the opposite. X is opposite of this angle cosine. So we're dividing by x here. So cosecant theta is square root of x squared plus 4 over x. We only have one place to write that. And that's in this part of the problem. And we swap it out. And everything's nice and clean. We're back in terms of x. And we've not forgotten our constant of integration. So very similar workflow, only a different form. That was the only real difference between this one and the last. And in here, of course, you know, this is where the 6.2a really shines, and you get some practice working with integrals of these trig functions, because of course, we'll see lots of them through trig substitution. Okay, another example, slightly more complicated, but just an algebraic trick to start this one. let's zoom in on our integral here. We want to integrate x squared over the square root of 4 minus 9x squared. And now the problem is, this is not a standard form. It's not a squared minus an x squared. And the problem is that 9, right? If this is sitting in front of x squared, it is not exactly like the form that we saw to begin with. Maybe a u substitution could change that, but that's really unnecessary, probably in most cases, in all cases, I would really say. What we can do is divide or factor a 9 away from this binomial. So in other words, we factor a 9 away from 4, and that leaves us with 4/9. Of course, double check that going the other way. 9 times 4/9 will give us a 4 again. So it's all there. Now, it's also been factored away from that negative x squared, when that was the whole point of doing it. Now we have a squared minus b squared underneath this radical, a squared minus b squared. This 9 is just a constant. We can move it around and get it out of the way and feel better about things in just a moment. In fact, we do that now. This is the square root of 9, so we can split a radical over a product. So this is really the square root of 9 times the square root of this term. And the square root of 9 is 3, and that's in the denominator. So this 1/3 comes out of the integral altogether. That was 1 over the square root of 9 is really where that 1/3 came from. And we pushed it all the way to in front of the integral because integrals are linear, and we can do that with constants. And we recognize we have a squared minus x squared as our form. And so we'll make the appropriate substitution. It's probably good to write down what a squared is in this. It's 4/9. So a is 2/3. Now that being the case, we have x equals a sine theta. So it's 2/3 sine theta. And now we want to take the derivative of x with respect to theta, or the derivative with respect to theta on both sides. That leaves us with dx is 2/3 cosine theta d theta. So now we've got our substitution for dx. The other thing we want to check and clean up right now is 4/9 minus x squared. Well, x squared is 4/9 times sine squared theta, if we just square that term. And that's exactly what we have here. This 4/9 minus 4/9 times sine squared theta. You understand now, hopefully, with these couple of examples, that this a in front is there so that these constants will match, and we can factor them away from all the terms underneath the radical. So we end up with 1 minus sine squared theta. We use that a times the trig function in each one of these so that we have a nice, clean Pythagorean identity term right here. We can swap 1 minus sine squared theta for cosine squared theta. And we have this underneath our radical. And of course, that simplifies to 2/3 cosine theta. And then lastly, we know that we have an x squared in our original problem. So we'll write down what x squared is right here. So we can sub that in our next line. So a lot of this is just setting it up for the substitution. In a lot of cases, we'll have some nice cancellations. Maybe not always. You might need a u substitution. We've seen that already. Or some good solid trigonometric integrals. But every now and then things cancel and they're nice. So what we have in this case is, here is x squared is 4/9 sine squared theta times dx is this term, all divided by the square root of, well, we worked all that out over here, right? Square root of 4/9 minus x squared really came out to a nice simple 2/3 cosine theta. So all our terms are cleaned up and ready to go. It makes facing this integral a little bit better when we do this work up here and simplify stuff a bit. So got a lot of constants floating around. Let's see if we can track some of them. We've got a 1/3 that showed up at the very front of this. And on my screen, it's a little hard to see why that's there. So maybe I'll leave that alone for now. But let's work with the constants that are in here. These 2/3 here are going to cancel. And we have 4/9 in front of sine squared theta. Also, cosine theta is going to cancel. So that's very nice. And we're just with sine squared in the integral with a factor of 4/9 as well. Let's keep moving forward here. So 4/9 can factor out and multiply against 1/3. We'll have 4/27 ultimately. And really, we're just dealing with the integral of sine squared theta d theta. And you can go back to section 6.1, integration by parts, to remember how to do this. We'll get some practice here. Hopefully, you've done this one so many times by now that you already know what the antiderivative is. But remember that the trick in this case, I'm sorry, this is 6.2a. Apologize. This is a matter of a trig identity. Sine squared theta, we're going to use the half angle identity. Sine squared theta is 1/2 minus 1/2 cosine 2 theta. 6.2a will show you through that if you look through those notes once again. And the reason we do it is because we need to get rid of that power of 2 of sine so that we can actually integrate this. Of course, this one takes a u substitution because of the 2 here, but that's not too bad. We can manage that. And that's exactly what happens below. We split this integral across this minus sign. So we have integral of 1/2 d theta for the first term minus the integral of 1/2 cosine 2 theta. And we see we've already made the u substitution. U is 2 theta. So du is 2 d theta. So then d theta is 1/2 du. You can see those details being worked out off to the right in the brackets. So we've got that laid out, and we have 4/27. The antiderivative times the antiderivative of 1/2 is just 1/2 theta. That's easy. And then the antiderivative of cosine u is sine of u. And then we just in this step have also backed out of the substitution. So we're back to sine of 2 theta. Of course, that was sine of u, and then swapped in for sine 2 theta. Factors of 1/2 gave us a multiple of 1/4 here. And then the integral signs are gone, so it's a good time to put plus c, our constant of integration. And our last bit of work is, again, of course, the triangle, right? We have this in terms of theta. This is in theta. We need this in terms of x. We've taken a step here to get halfway there. Let's go back and look at the triangle. This is sometimes the trickiest part for students. Remember, you draw a right triangle with theta and some base somewhere, and that's it. You start with that. Theta is some right, and an angle in some right triangle, not the 90-degree angle, of course. And then we look and say, what do we know? Well, we know that x is equal to 2/3 sine theta. That's our key. It's always the key to getting back out of this. So sine theta is equal to x divided by 2/3. Well, x divided by 2/3 is 3x/2. If you work out the algebra of that, you should find that this is the case. So if sine of theta is 3x/2, we can label our triangle as opposite 3x over hypotenuse 2. And then our last leg, we use hypotenuse squared minus this leg squared, square root of all of that. And so we have square root of 4 minus 9x squared. Again, we see that show up. It's reassuring. We probably got things correct so far. Okay, so those are all the sides of the triangle, but notice we now need to know sine of 2 theta. That could be somewhat problematic until we remember that there's another double angle identity around, and that's sine 2 theta is 2 sine theta times cosine theta. So if all this trig is really freaking you out, let's go back to some of the end paper in the book, or look up some trig identities. You're going to want to write down all the Pythagorean trig identities and all the double and half angle identities. Well, more importantly, the double angle identities. And that should get you by for now. Don't panic. That trig will come back to you. This is what we need in this moment to write down what sine of 2 theta is. And it's sine of theta times cosine theta with a factor of 2 out front. Sine of theta, we already know, that's 3x/2. We could get it from the triangle too if we wanted. And cosine theta, we look as adjacent over hypotenuse, and that gives us this fraction right here. So some cancellations, we'll clean that up, but we see this term injected down below, and we've got sine of 2 theta written as follows. That 1/4 was just the factor that was already there. Now a little further, we need to find what theta is, and that one actually turns out to be a little bit easier. You see that it's sine inverse of 3x/2, and you might have gotten that. Well, we see it directly here. To solve for theta in this, we just take the sine inverse of both sides and we get that. It's not anything special, not anything fancy, so it doesn't evaluate to anything clean. We have to have sine inverse as a function written in our answer, but that's just fine. That'll be the nature of a lot of these problems. So there it is. That is another a squared minus x squared problem. We did not see an x squared plus a squared problem. I don't believe in this, or maybe we didn't see an x squared minus a squared. It's just a matter of using secant then. But the workflow is the same for all of these types. Just be sure to recognize what form you're dealing with. And if it's not quite the correct form, to make a little adjustment on that constant, just as we did in this problem. It's about as hard as they get. You might find some with some tricks that you might not catch right away. But if you can do problems like this, you're probably pretty well off. Certainly practice all of them. But let's see one last one. It's quite a bit easier. We don't see many definite integrals in the notes. So of course, I like to cover one every now and then just to make sure we don't lose track of that. But we're asked to find the definite integral from 1 to 2 of this rational expression here. And well, the first thing to realize is that we've already integrated this as an indefinite integral. So if you go back to example, I believe it was 3.2, it might have been 3.1 actually, but at any rate, oh no, it was 3.2. That's correct. You go back to example 3.2 as the note says, and you find that the antiderivative of that function, the indefinite integral, was this. So if you had to carry that out, you'd want to come all the way back to x, right? You start in x, these limits of integration are in x. Don't get lazy and do this in terms of theta. It will be wrong. So do this in terms of x, come all the way back to x. The one thing you could do if you like is to change these x coordinates to coordinates in theta, or at least these x values to values in theta, but you're going to have to do inverse trig function work there that you might not like. So you come all the way back to x, then you plug in your limits of integration. And again, of course, evaluate this function at 2, that's this portion, minus evaluating this function at 1, which it looks backwards because the minus sign has already been pushed into there. So we flipped the role here. So this is the evaluation at 2, but it's negative because of the minus sign, minus the evaluation at 1, which is positive because of, well, the minus sign. So that's maybe too many steps in one move there, but maybe I'll leave it to the reader to inject this intermediate step between the two and see that that's in fact the case, if you have any questions about it now. And then of course that simplifies to what we have below. So be careful, you're probably gonna have to go all the way with most of these definite integrals. So don't be lazy and make mistakes with theta and not back out completely. So that's it for 6.2. A was trig integrals. B was trig substitutions. Of course, you need trig integrals strongly before you're more solid with trig substitutions. But practicing both of these is really the key to this whole section.